Hello, welcome to another lecture in Physics 2. We're going to talk about optics, and we're going to continue discussing electromagnetic radiation, but we're going to kind of focus on the properties of light, which is, remember, a very narrow band in the electromagnetic radiation spectrum. So we're going to look at some properties of light and what happens to light when it interacts with other media, right? So in chapter 22, we looked at electromagnetic radiation in vacuum, which is the absence of anything, right? Vacuum is like air with no molecules in it. It's just nothingness, emptiness. So we're now going to look at what happens to waves when they interact with stuff. So this branch of optics is called physical optics. So we're going to look at the wave nature of light. We're going to talk about a concept called Huygen's principle and how it explains the way light reflects and refracts off of new media. We're going to discuss a property called total internal reflection, and we might get into the dispersion of light in this lecture. I have 3 parts delegated to this chapter because it's pretty lengthy, so depending on how long the video gets, I might include 23.4. So we're going to hit the first 3 to 4 sections in this video. And the rest of the chapter is just other properties of light, how it interacts with thin films, interference of light waves, right? Remember interference from when we talked about mechanical waves in Physics 1. So we're going to take that concept and apply it to electromagnetic waves. So to review, I think the most important thing to review, and you won't need it for this lecture video, you'll need to take a look at the constructive and destructive interference of waves for mechanical waves, and the same principles apply to electromagnetic waves. So this is going to be important for when we get to section 6 of this chapter. So let's kind of provide some motivation for this study. Right? How does light waves behave in nature, right? We're not considering vacuum any longer. You know, when we look at waves in vacuum, it's a very idealistic case. As you know, the world around us is mostly non-vacuum, right? There are molecules everywhere. There are materials everywhere. So we're going to explore how the wave nature of light interacts with all of these different objects around us, and we're going to kind of stop talking about electric and magnetic fields, right? We don't really need to know that microscopic information anymore. We're going to kind of zoom out and look at the properties of light, from a wider perspective. Although electric fields will come up briefly when we get to polarization, okay? So we will kind of briefly talk about electric field again when we get to polarization. But many of the properties of light that we will encounter in this chapter actually apply to many other types of waves, like mechanical waves, sound waves, okay? So these are just the properties of waves. But we're going to take a look at light specifically. So in this chapter, we're going to discuss Huygens' principle, how light reflects off of objects, how light refracts off of objects. We're going to discuss dispersion, interference and diffraction and polarization. For this particular video, we're going to hit these first 3 topics, possibly dispersion. And here's some examples, interesting effects that light has. I think you've all seen either pictures, videos, or in real life, the kind of reflective eyes that cats and even dogs can have. And there's a purpose for that. So these animals, well, cats in particular, They are nocturnal, and they need to be able to see in very low light. So the reason they're able to do that is because of this layer of their eye in the very back of their eye, and the reflection that you see is you see an opaque reflection, right? His eyes look opaque and yellow because what the eyelid or this layer of the eye is doing is it's allowing the light to enter the eye and keeping it trapped inside of his eye so that he can use that light to see better. So what we see is kind of like an opaque reflection, but what's happening is it's opaque because the light is being able to be reflected inside of his eye. So the colors of the rainbow are caused by a property called dispersion, which we'll get to in this lecture video. And this dispersion happens, so dispersion, disperse, right? What's happening is white light is a combination of all the different colors. And when white light passes through a different material, for example, water or wet air, humid air, the frequency of light changes and its path changes as well. So what happens is we see the red light occur up here and the purple light occur down here, and of course everything in the middle gets dispersed, right? So you kind of see the separation of all the pieces of white light. And then we'll talk about thin film interference. So we get kind of this dispersion effect again, but this is through a very thin film, and it's caused by a totally different property. It's caused by interference, okay? So it's kind of a rainbow thing again, but the reason behind this rainbow is different than in part B. So just really, we're motivating our study for this section, right, for this chapter. And the key, in essence, the key properties of light can be understood by the wave properties, okay, by considering light as a wave. So we're going to talk all about that. The first thing we're going to do before we get into Huygens principle is let's define what it means for light to be reflected and refracted. Okay, so as light travels, it travels in a straight line. And if it were to encounter a material, which we would call the medium, okay, it can do one of two things. Well, it can do both things, actually. So those two things it can do is reflect off of the new medium or refract into the new medium, okay? So a reflection would occur at the boundary between the old medium and the new medium. So in this picture, the old medium or the incident medium would be air, and the new medium would be this yellow liquid, right? You can use your imagination and maybe come up with what this yellow liquid could be. So refraction is when the light changes its direction, right? It's no longer traveling in a straight line. It changes its direction and kind of tunnels into that new medium. That's refraction. Reflection is, exactly what it sounds like. It reflects off of that boundary, right? This is the boundary between the old medium or the incident medium and the new medium, okay? So in general, both things occur, right? Some of the light gets reflected and some of the light gets refracted. And so there's some angles defined here. So let's take a look at these angles. Theta 1 is the incident angle, okay? So we call that the incident angle, and it's defined just as every angle that we have talked about up until this point. It's defined with respect to a normal. And in this case, the normal is the normal to the interface or the boundary between the two media. So, right, it's 90 degrees. This normal is 90 degrees to that boundary between the two media. the air and the mysterious yellow liquid. So theta 1 is the incident angle, and the law of reflection, which will be the first law that we're going to learn about in optics, states that the angle of reflection is equal to, the angle of reflection, this guy, is equal to the angle of incidence. So it's a very, very basic, simple law. So whatever angle the light is incoming at with respect to the normal, it will be reflected at that very same angle with respect to the normal. And this is always true. So refraction, the law of refraction is a little bit more complicated. I'm not going to introduce it yet, but what I want you to know is that the angle of refraction is defined with respect to the normal, and we call this theta 2, okay? And the 1s and the 2s are because we call the media, the incident media 1, and then the refracted media 2, or the second media 2, okay? So that's where the 1 and the 2 come from. So, and then in general, the refracted angle, theta 2, is not equal to theta 1, okay? It's not ever going to be equal to theta 1. And we'll talk about what the relationship is. But first, what I want to do is introduce, after we've kind of laid out the groundwork, let's talk about what Huygens principle is. And the pre-lecture video does a really good job at explaining it. It's a bit of a conceptual, kind of weird principle. So what it states is that waves that travel in 2 or 3 dimensions, for example, like plane waves, right, that we discussed. Remember, electromagnetic waves are plane waves. They have a certain property, and what that property is that for each wave front, right, so this is a plane, okay, so which we'll call a wave front. You can imagine that at every point on that wavefront, even the ones not pictured here, act as a new source of that wave and then produce their own wavefront. Okay? So that's what Huygens principle states. It says, okay, you have a source of an electromagnetic wave, such as a light source. So maybe this is a laser or something, or a light bulb, and all the waves are going to be traveling directly away from that light source, right? So these arrows are going to denote the direction of the propagation, which would be the velocity's direction. And anywhere that you find, that you cut 90 degrees to those, which would be the plane of the E and the B field, any location on that plane can be thought of as a source of a new set of waves. And this is important because this explains how those waves travel in space. Okay, it explains these circular wavefronts that we have observed in experiment. And so the way to visualize this is think of a rock or a drop of water hitting a pond, right? The drop hits right here, and then what we see as a result is these ripples in the water, right? These circular ripples. Well, these circular ripples are analogous to these wavefronts of our electromagnetic radiation, right? Which could be light or any other frequency. So these wavefronts spread outward in a circle from its point of origin in the same way in Huygens principle, okay? So using this idea, we can derive both the law of reflection that we already talked about and the law of refraction. So that's what is done in the next 2 slides. I believe it's in the pre-lecture video, so I'm not going to talk about it here. You can take a look at the pre-lecture video. I'm not going to be testing on the derivation, but I just want you to know the connection. The connection is that this principle, Huygens principle, allows us to figure out how reflection, the law of reflection occurs, and the law of refraction, okay? So watch the pre-lecture video to see the connection between Huygens principle and reflection, and then there's another pre-lecture video that derives the law of refraction. It's a little bit of geometry, and I put some figures here that show the geometry and how it allows us to find the law of refraction. So remember, I didn't tell you what the law of refraction is yet. So you start off with the two plane waves, right? The two wave fronts. And when that wave encounters a new medium, remember when it's refracted, it bends at an angle not equal to the initial angle, right? So when you take a look at these two triangles, I'm just kind of briefly going over what the derivation does, but I'm not going to make, I'm not going to test you on it, right? What you can do is these two triangles, you can compare them using the law of similar triangles. And what you find out is you find this relationship right here, where sine of theta 1 and sine of theta 2 are equal to each other, but differ from a factor of 1 over v1 and 1 over v2, where v1 and v2 are the speed of that wave, right? v1 is the speed of the wave in media 1, and v2 is the speed of the wave in media 2, right? So this is the sine of the incident angle, remember, which is always defined with respect to the normal. This is the sine of the refracted angle. This is the speed of the wave when it's in media 1. And this is the speed of the wave in media 2. So it's a little bit more complicated relationship, right? It's not simply theta 1 equals, theta 1 prime, the reflected angle. We have signs going on, and then we also have the speed of the wave factored in there. And so what we can do is, this is one expression of the law of refraction, but the most common way we express the law of refraction is by converting these velocities to another parameter, where the parameter is called the index of refraction. So the index of refraction, which we denote as the letter n, lowercase n, it's the ratio of the speed of the wave in vacuum, which is the speed of light, right? For any electromagnetic wave, not just light, but any electromagnetic wave travels at c when it's in vacuum. So the index of refraction is the speed of light divided by the actual speed of the light in that particular medium, okay? So this is a ratio, so there is no units, right? No units for index of refraction. And the units of this are obviously meters per second and meters per second, right? So the index of refraction is a ratio. And the index of refraction is always going to be a number greater than 1. And why is that? Because nothing can move faster than the speed of light, right? So the speed, the velocity v, is always going to be some number less than the speed of light. So you take a big number divided by a small number, you're going to get a number greater than 1 on the left-hand side, right? And so another way to think about it is we can solve for velocity. Okay, we can solve for velocity. And since n is always bigger than 1, c divided by n, a number bigger than 1 is going to be some number smaller than c, okay? Which is basically what this statement says right here. So what is the index of refraction of a material that is vacuum? Well, it's equal to 1 because the speed of light in vacuum is is C. So C over C is 1. All right, so we're going to now rewrite the law of refraction. We're going to substitute velocity for this expression. And when we do that, we get n1 over c on the left and n2 over c, right? Because 1 over v, which was what was there, is equal to n over c. Right? We just kind of rewrote that guy, right? And so then, well, the c's will cancel out. And now we have what's known as Snell's law, which is the law of refraction written in terms of the index of refraction instead of the speed of the wave, but both are equivalent, right? Both expressions are equivalent. And you may need to use one over the other depending on what kind of information you're given in the problem. So don't neglect, this equation up here, right? Or, here they are written at the same time, right? So they're both equal. So you might need to use one over the other depending on what information you're given in the problem, okay? So when it's written in this way, this is called Snell's law. And it was named after a Dutch scientist who, for a while, we thought that he was the first person to discover this, but as usual, most of, math and a lot of physics was actually discovered, hundreds of years prior to, all the quote white guys from Europe, right? That were real busy in the 1800s. This is an example of that. So a Persian scientist is actually the first person who observed this refraction law. Okay, so you're gonna find that a lot, and we must always give credit where credit is due, right? Algebra is another perfect example. Algebra, right, was founded, hundreds of years before anyone started working on it in Europe. So going back to the index of refraction, right, we saw that the index of refraction is a ratio between the speed of light in vacuum and the speed of the light in whatever material it's in. So let's look at some materials and their indices of refraction. And let's kind of think about what does that even mean, right? So vacuum has an index of refraction of 1, right? Because the speed of light in vacuum is c. So we would get c over c, which is equal to 1, right? Air, you can see, is pretty darn close to 1. So the speed of light in air is really close to the speed of light in vacuum. And as the material changes, okay, and gets more complicated with more molecules and a better organization, meaning like a crystal structure to it, you can see that the index of refraction increases, right? And what does that mean for the speed of the wave in that material? Well, the speed of the wave will decrease, right? And that kind of makes sense because as an electromagnetic wave goes through some material, if that material has a lot of different molecules and atoms in it, it's going to start interacting with the light and slow it down, right? So it makes sense that the velocity of the light will decrease as the index of refraction increases. So that's an important relationship. Let's look at some cases, okay? Let's look at a case where the incident material, which has an index of refraction n1, so the 1 will denote the incident material. Let's look at a case when the incident material has a index of refraction smaller than the material, the refracted material. So in other words, we're looking at when n1 is less than n2, okay? And since we know the relationship between n and velocity, what we're saying is that the velocity in 1 is greater than the velocity of light in medium 2, right? And so what happens to the refracted angle? Well, the refracted angle actually gets smaller. So theta 1, let me kind of scoot this over here. Theta 1 gets larger than larger than theta 2, or in other words, theta 2 is smaller than theta 1. And the light bends toward the normal, right? Because the angle is with respect to the normal. So if theta 2 gets smaller, then the light is bending toward the normal, okay? And that's what happens when light goes from a medium where it moves quickly to a medium where it starts to move slower, okay? Let's look at the opposite case, okay, over here in this box. What happens when light moves from a slow medium to a fast medium? Well, that means that the index of refraction of the second medium is smaller than the first, which means the velocity of the second is greater than the velocity of the first, and the angle of the second is going to be greater than the incident angle, right? So if the angle is greater in the second medium, what we say is that the light bends away from the normal. So these are important relationships to go back to, okay, and fully commit to, I don't want to say memory, but, to really understand the concepts for these two relationships, right? Going from a slow to a fast and a fast to a slow, relating that to the index of refraction, relating that to the angle of refraction in relation to the angle of incidence. So how is this, let's kind of why is this important to us in the biomedical field, or those of you going into chemistry? We can use optics to characterize materials, okay? And it's a really important method for material characterization because it's typically non-invasive, right? It doesn't alter the properties of the material it's investigating. So optics is a very important branch in any kind of field, really. Even in physics, it's a very huge field. So what happens is when light is incident on a new material, some of it is refracted, some of it is reflected, and if you can measure the angle of refraction, then that can tell you about what the index of refraction is in that material. And the index of refraction is very oftentimes easily related to the density of that medium. So one example is blood plasma, how many proteins are in the blood. Another example is how much sugar is in wine, right? The more sugar there is, the more dense the wine is. And so if you can just send in some light into a, clear box of wine or blood, and you can visually see what this angle is, well, then you can figure out what N2 is, right? So this is just one example of how optics can help you in science, right? And the benefit is that this light typically does not alter the material that you're measuring, okay? And if it does, then you can just choose another wavelength, right? So you have a wide range of options here. So let's do an example, okay? In this example, I'm not going to say it's complicated, but there is a concept in here that, you know, may seem strange to you, but once you know it, you got it. So let's say you are a surveyor and you're looking at an aqueduct, which is simply like a pool of water, okay? And when you look into this pool of water, you are looking at the corner and you happen to know that the width of this aqueduct is 4.2 meters. And the question is, if we know that, and if we know like our line of sight angle, can we figure out how deep the water is? So the concept part of this, that, you know, once you understand this part, this question will make a lot of sense. The concept part is, take a look at this, the direction of this red arrow, right? It's coming from the corner of the aqueduct and going to her eye. So when you look at something, I don't know if you knew this, but when you are looking at an object, your eye is like not sending out light rays, right? And then the light is bouncing off of that thing and going back into your eye. A light source is sending out light rays. For example, the sun, a light bulb, right? So let's say the sun is out, allowing her to see. And what's happening is the sun sends out its own light rays everywhere, right? Everywhere. Some of it is going to strike this point and bounce off of it and go to your eye. So your eye is actually seeing a light ray that has reflected off of whatever it is that you're looking at and is entering your eyeball. And so with that in mind, let me just erase this one. With that in mind, what is the incident material and what is the refracted material? The incident material is going to be water, right? Because that is where the light is coming from. And the refracted material is going to be air. Do we see that? Because the light that the objects that we see are light rays that have come from somewhere else, like a light source, reflected off of that point that we're looking at, and then make it to your eyeball, right? So when she is looking down at the corner of this aqueduct, the light ray is actually coming out of the water into her eye. And so when it's traveling in a straight line in the water, and then when it hits this new material, right, it no longer travels in a straight line, it gets bent, it gets refracted. So let's see if we can calculate what the depth is with a little bit of geometry. Well, we're going to need to use the law of refraction. So let's go ahead and write that down. N1 sine theta 1 equals N2 sine theta 2. But remember, N1 now is going to be the water. And I just happen to remember that the index of refraction of water is 1.33. If you didn't remember that, you could look back at the table. But I'll be providing, you know, in exams what the index of refraction is. So you don't have to spend time looking at a table. So N1 is water, 1.33. N2 is air, which we'll just say is 1. Okay. It was 1.0029, but, you know, to 2 decimal places, it's 1. And so what else do we have? Well, we're given, we're kind of given the angle of refraction, right? We're given 25, but the normal to the interface or the boundary is here, right? So we need, and we can actually draw it here as well. So what we need is we need theta 2. We're given 25, so we need to convert that to the angle from the normal, which would be 90 minus 25. So we know that theta 2 is 90 minus 25, which is 65. And so, well, now we can solve for theta 1. And then let's see what we can do with theta 1 to help us find out what the depth is. I need to rewrite that. So we have water sine theta 1 air sine 65. And so we can solve for theta, sine theta 1. And then that's going to end up being in sine inverse okay. Plug that into our calculator. Grab it. Make sure you're in degree mode. I know you had to be in radian mode for the last exam for a lot of things, so make sure you're in degree mode. And what I got was pretty much 42.96 degrees, which, you know, we could call it 43 degrees, right? So that's theta 1. That's not exactly the target variable, right? We're looking for the depth. So, well, we can easily find the depth because you can see that this guy is a right triangle here, right? It's a right triangle, and we know the width of the aqueduct. So now we know this angle is 43. We know that this side is 4.2 meters, and we can solve for D. The best way to do that is probably using tangent, right? Tangent theta is opposite over adjacent. So that means that tangent of 43 is going to be opposite, which was the 4.2 meters over D. Now we can solve for D. And we get D equals 4.2 meters divided by tangent of 43 degrees. And that's 4.5 meters. So the depth of the aqueduct is 4.5 meters. So that is the actual depth, right? That is the actual depth. But what does your brain actually think? So this is kind of interesting. I don't know if you've looked in a pool, or maybe you've looked at your straw in a glass and you kind of see that it looks funny, right? So this is another important concept that we will talk more about in the following chapter, in chapter 24, but now is a good time to bring it up. When your brain is like, it's smart, but it's not smart, right? The smartness is in certain areas of your brain, the part that knows what the law of refraction is, right? Now you know what the law of refraction is, but your eyes and the place in your brain where your eye sends information does not know what the law of refraction is. And so when your eye sees something, it assumes, and your brain assumes, that the light ray came from straight back, right? It traced a straight line. So your brain basically traces the light ray straight back, okay? It doesn't know that the light bends when it gets into water. Like, that's a totally different part of your brain that knows that now. But the part that receives eye information does not know that. And so when the surveyor lady is looking at the aqueduct, it's going to actually look shallower than what it really is, right? Because the brain is tracing the light ray back to this point, which is a shallower depth. So this question, a similar one, I've seen it on the MCAT before in previous years. So that's kind of why I like spending a lot of time on it. This is called the apparent depth, right? So the apparent depth would be the depth that is kind of like what your brain thinks, but the actual depth is the one you would calculate using the law of refraction, okay? So this is a really good example. This kind of goes into what we just talked about, right? Our brains are used to the idea that light travels in straight lines. The part of your brain that receives information from visual information does not know that the law of refraction exists. So if we extend that light ray that reaches our eye straight back, it actually comes from a different location. It comes from a shallower part of the aqueduct, right? So the apparent depth of the pool is less than the actual depth. And this is a very common thing that you have seen a lot. So for example, if you have a straw or a chopstick in a glass of water, I don't know why you pick a chopstick in water, but a straw, right? You put your straw in a glass of water, and you notice that the part that's submerged in the water is like in a totally different place than the straw itself, right? And the reason for that is because your eye is like receiving this information, and it's tracing back the light ray to a different position because it doesn't know that the law of refraction exists, right? So this is another example of the apparent depth, okay? So we talked about refraction. What else? So what happens to the light wave when it enters a new medium? Like, does its properties change? Well, we know that its speed decreases or increases, right? So we know that the speed of the light changes. So how does that affect the frequency and the wavelength? So that's what we're going to get into. So when light or any electromagnetic wave travels from one medium to another, the frequency remains the same, okay? So that's the key concept here. The frequency does not change. And the reason for that is because the frequency tells you how many crests or how many peaks or troughs of that wave is going to arrive at the boundary in a certain time interval, right? And if you think about it, the amount of waves that enter a boundary must equal the amount that leaves the boundary, okay? So if the frequency were to change when the light wave encounters a new material, that would affect how many waves are leaving. And since they must be equal, right? Because the wave is not, we're not creating or destroying the wave and how many are entering the boundaries, how many crests are, that must remain the same, and therefore the frequency must remain the same. But something has to change because the speed is changing, and we know that this speed is equal to frequency times wavelength. So if the speed is increasing and the frequency remains the same, well, guess what? The other guy, the wavelength, must change, right? And so it's going to change proportionally. So proportional to f. So if the velocity increases because we're going into an index of refraction that's smaller, then the wavelength will also increase, okay? If the speed is slowing down because we're going into an index of refraction that is bigger, well then guess what? The wavelength will also go down because the frequency must remain constant, okay? So that idea can be translated into an equation that expresses the new wavelength of the light as it enters a new medium. We start off with the fact that we know what the wavelength of the light is in vacuum because the speed is c and the frequency is the frequency. So we know the wavelength of light in vacuum. And if the new medium has an index of refraction n, then we know that V equals C over N. So we can combine those two equations to this guy right here. Okay? So the wavelength of the light in the new medium is going to be equal to the wavelength of the light in vacuum divided by the index of refraction of the new medium. And we can rewrite the wavelength in vacuum as C over N, or C over F. So we can have two expressions for the new wavelength, okay? And so what this equation says is that, the wavelength gets shorter for a medium with a higher index of refraction because the speed is slower, right? So what we said in the previous slide was as V decreases, lambda decreases. But if V decreases, that means the index of refraction is bigger, right? And then vice versa is true. If V is increasing, it's speeding up because the index of refraction is getting smaller, and therefore the wavelength will also go up with velocity. Okay, so think about those relationships. In the beginning of this chapter, there's a lot of relationships. So think about it. Make sure that you can say it as reproducibly as I can, right? By the time the exam comes around. So let's wrap up this section with this conceptual problem. Let's say we have a beam of light, all right? It's in air, starting off in air, and it has an incident angle of 5 degrees, and then it goes into some plexiglass. And then from the plexiglass, it goes into some water. In each refraction, does the ray bend closer to the normal or farther away from the normal? So let's draw a picture here. I'm going to draw the two boundaries, right? Here we have air, here we have the plexi, and then here we have the water. And I'm going to draw the normal to the interface, because remember, all of our angles are with respect to the normal. And then I've written all of the indices of refraction here, so we don't have to waste time looking it up, okay? And so the initial angle is 5 degrees with respect to the normal, so let's just pretend that that's 5. And so going from air to plexiglass, the index of refraction is increasing. So therefore, if we go back to those slides, what does that tell us? If the index of refraction is increasing, then the angle of refraction is going to bend toward the normal, okay? It's kind of like opposites. So the relationship between n and the refractive index is opposite, okay? So here it'll bend toward. Or go closer, using the words of, right, go closer to the normal. And so now we're going from 1.49 to 1.33. So n is decreasing, and, well, the opposite's going to happen, right? If n is decreasing, then theta 2 is going to increase. So now we're going to bend away from the normal. So we can draw another normal right here. And then theta 2 is going to bend away from the normal, or go farther from the normal, or go away, right, from normal. So which one of these options is going to explain that? So it's not going to be A or B. It looks like it's probably going to be C, closer to the normal for plexiglass, and then farther away when it goes from plexi to water, right? We can check the other options just to make sure. Farther away, and then that's the opposite. Nope. And then in at least one of the refractions, the light does not bend at all. No. Okay, so it's definitely C. Okay, so this is got the concept question. You could definitely, get something like this on the exam that talks about the relationship between the index of refraction and the refracted angle, or maybe it could be changed to mention the speed instead of the index of refraction. Okay, so to wrap up this section, we briefly talked about Huygen's principle, and basically Huygen's principle explains how we can figure out the law of reflection and the law of refraction. And I spared you guys from the derivation. Okay, so just accept what those laws are, right? The law of reflection, remember, is simply the incident angle is equal to the reflected angle. And the law of refraction, also known as Snell's law, is N1 sine theta 1 equals N2 sine theta 2, right? So that, and then we looked at a bunch of relationships, you know, between wavelength, index of refraction, speed of the wave, refracted angle, right? All these relationships. So those are important. So we're going to look at total internal reflection. And it's a special case of Snell's law. So let's kind of observe what it is first, and then we'll take a look at the math that describes it, right? So in this figure, we see a piece of glass, and then we see like light going through the glass, right? Let's say it starts over here, and then it enters the glass. So it's in the glass, and it's going to reflect off of this boundary between the air and the glass. And if you can see here, all of it gets reflected, and none of it is refracted, right? You don't see any light beam here. None of it, or here, right? None of it is refracted. And for this situation, we're going to ignore, I want you to ignore this part and this part, right? We're only looking at light that is starting off in the glass, okay? So basically, what are we saying? N1 is glass. Okay, so we're saying that this is N1 and that this is N2. And this is a very important concept behind total internal reflection. So the light is incident in the glass. Obviously, we have no way of making light in the glass, so we have to kind of like shine it from this way. So we're ignoring that part. When it's incident in the glass and it meets this glass air boundary, you can see that all of it's reflected and none of it's refracted. And so this is called total internal reflection. So since all of the light is reflected back into the glass, none of it goes into the air, what is this telling us? This is telling us that the index of refraction of the first medium, which is the glass, right, and sine of that incident angle, which we're going to call theta c for now, is equal to the index of refraction of the air times sine of 90, right? Because technically, where is this refracted light, right? None of it's here, none of it's here, none of it's here. You know where it is? It's actually going down this way. It's getting refracted at 90 degrees, okay? Right, so if this is the normal to that interface of the glass air, so, realize that the normal doesn't have to be up and down. It can be left and right if the boundary is rotated, right? So if this is the normal and then theta 2 is always with respect to the normal, well, then theta 2 is 90 degrees, right? And so if we plug in theta 2 equals 90 here, we're going to end up with sine of 90 is 1. And what we see is that the law of refraction ends up just equaling N2, right? So we can solve for the incident angle here by isolating sine of theta c, right? Which would become N2 divided by N1. And what you find is that this angle in the glass, the incident angle in the glass, so where's theta c here, right? It's with respect to the normal. So let me go ahead and write that down. Right, here's our normal. So this theta c, the incident angle in the glass, is creating total internal reflection, okay? Because the refracted angle is actually 90 degrees. And so that means all of the light is being reflected back into the glass. And this can only happen, and this is why it's so important to denote what was N1 and what was N2 up here, okay? This only happens when N1 is greater than N2. So we can see that mathematically because we know that sine of any angle between 0 and 90 is going to give you a value between 0 and 1. And so if the right-hand side has to be a value between 0 and 1, Well, that means that N1 must be bigger than N2, right? Because, or else we would get a value greater than 1 on the right-hand side. So if N1 is greater than N2, then the ratio N2 over N1 is less than 1, and there will be some angle, incident angle, called the critical angle, for which this equation up here is satisfied, okay? And this is a case where total internal reflection is possible. It is possible for sine of 90, the refracted angle to be sine of 90, and total and everything to be reflected back inside of that incident material. However, though, if N1 is less than N2, well, then this ratio is greater than 1, right? And there is no solution, right? If you do sine inverse, if you were to put in your calculator sine inverse of 1.01, you would get, let's see, what does my calculator say? What language does it decide to use to tell you that's wrong? It says undefined, right? Undefined. That's undefined. There is no solution to that, right? So, in other words, total internal reflection only occurs when the initial or incident material has an index of refraction greater than the second material, okay? So, glass, air, alcohol, water, right? You can take a look, go back at that, go back to this table, and you can see all the combinations where total internal reflection can occur, right? Sugar water and water, you know, where the incident material is crown glass and ice. So, right, you have to start off in the bigger index of refraction and go into a lower one in order to possibly get total internal reflection. So that's essentially what total internal reflection is. So we can solve for theta c by taking sine inverse, right? And this is going to be called the critical angle. This is the angle for which light incident in medium 1 encounters a boundary with a lower index of refraction, and that creates all of the light reflecting and none of it refracting. Okay? So here's another example of total internal reflection in water, right? So if I shine a light, you know, I have to shine it from out here, but now it's incident in the water once it reaches that boundary, right? It's incident in the water. Water has a higher index of refraction than air. And so what's going to happen here, if I shine it at a certain incident angle, then I'm going to get no refraction. Well, technically what I'm going to get is I'm going to get my refraction occurring at theta 2 equals 90, right? Technically, I mean, you know, I get no visible refraction because the light is being refracted along the boundary. So, so this is the case of total internal reflection, right? With just two different media, water and air. So, and this works because the index of refraction of water is greater than that of air. So, in this example, we can figure out what these angles are. So if the laser is incident in water, let's find the critical angle where total internal reflection can occur. So we can write down theta 2. N2 over N1. And right, N2 is the refracted or the second material, and N1 is the incident material. So we're going to have 1 over 1.33, and this is going to work out for us because that's going to give us a number less than 1. So let's go ahead and figure out what that angle is. And it's 48.75 degrees. And so that's the angle that we need to shine the light at in order to get total internal reflection. So what if we change the water to sugar water? Okay. So if we are now going from sugar water to air, we're going to do the same thing. Okay, but now N2 is going to be sugar water. And I don't recall what sugar water index of refraction is, so we can just look up here. I'll always provide you the values in the exam, so don't worry about it. It's 1.49. I had a feeling it was that, but I forgot. 1.49, same as plexiglass. Interesting. So N1 is 1.49, right? It's the sugar water. So we can figure out what the critical angle is. So we would do 1 over 1.49. And so we get an angle of 42 degrees, 42.2 degrees. Okay, so, when it comes to total internal reflection, obviously the math is pretty easy. What the concept is really what is the most important part, and that's just remembering that the initial medium must have the higher index of refraction in order for total internal reflection to occur. Okay, so interesting. What a mirage is, a mirage can be explained by total internal reflection. So let's say you're looking, down a hot road. It's a hot summer day. The road is hot, and it looks like there's water on the road, right? It looks like there's puddles of water. But what you're seeing is not actually water. You're seeing the sky. Okay, the sky, it has the color of water, right? So you're seeing the sky. And so why are you seeing the sky down there? Okay, on the road. So the explanation for that is when light travels through hot air, right, the index of refraction of the hot air is going to be higher. So because it's more dense, right? And that's going to constantly refract the light. And it's going to refract it so that its angle of incidence when it eventually reaches the road is super small. And when that light reflects off of the road into your eyeballs, well, remember what your brain does, right? Your brain doesn't know about the index of or about the refractive law. And so it's going to trace back that picture of the sky and project it onto the road. And your eye is going to think that the sky you're looking at is on the road. And that's what a mirage is, right? You're seeing essentially the sky being projected on the road because of how your eye traces back light rays straight back. And it got to that point to begin with because the light is entering a higher and higher index of refraction as it gets closer to the road because it's getting warmer and warmer down there. And that makes that initial angle of incidence small enough to meet the conditions for total internal reflection. Okay. So that explains mirages. So another important application of total internal reflection is basically using fiber optics. So we use fiber optics to, right now we're actually using it for internet speeds, right? You can get really fast, reliable internet using fiber optics. For example, Frontier has been installing fiber optic cables in my neighborhood. So another application of using these fiber optics is in a procedure called endoscopy. And so basically, endoscopy is when we image inside of our body by feeding like a wire through your nose or through your mouth or through some other orifice, okay? The possibilities are endless here. And so the way that we can actually see what's inside of our bodies, even though it's super dark, is we send a fiber optic cable down there and we send light through that cable. And if total internal reflection was not occurring, then the light would refract out of the cable and we would lose the brightness, right? It would keep refracting, and it would lose some of its brightness. So instead, this fiber optic cable has a higher index of refraction than the air or the body around it. And so the light keeps reflecting, and it stays nice and bright until it reaches wherever we're trying to image, right? Because we want to shine some light so we can actually take some pictures. So the fiber optic cable is keeping the beam inside of the fiber all the way to the point where we need it, which is to kind of take a picture deep inside the body. And so what you'll see is if you ever get an endoscopy, there's actually going to be several cables kind of bound together. One will be for the bright light, one will be for the camera feed, right? And one will be maybe to control the movement of the camera or something. So, and we use basically the property of total internal reflection in order to maintain the latency, right? Which is like the strength of the light, so that we don't have interruptions in camera feed, right? By the light or the camera feed leaking out. So it's very important biomedical applications as well. So let's go over this. Oh, there's the answer, but let's go over this, got the concept. So it's about total internal reflection. So let's say that it's possible for a beam of light within plexiglass to undergo total internal reflection at a boundary. And it can do that if the material on the other side is what? So here's the table. And so we can write down the index of refraction of each material here. And so what's the condition that we're looking for? Well, total internal reflection only occurs if the incident material has a greater index of refraction than the outside material, right? Remember the picture we saw, we had glass and then air outside. So the question is, if the initial index of refraction is plexiglass 1.49, which of these N2s has a value greater than 1.49? And it looks like sapphire and diamond are the options. So the correct answer would be more than one of these. Okay, nothing too crazy here. So to wrap up this section, we looked at a special case of Snell's law, right? Which is total internal reflection. And that special case is that all of the light is reflected, and any light that is refracted, it's refracted at 90 degrees. So theta 2 is 90. And so then theta 1 becomes our critical angle that allows total internal reflection to occur, and we can easily solve for that. And the main concept behind this is that the incident index of refraction must be greater than the index of refraction outside of that material, okay? So I'm gonna save this for another video, and we'll pick up from there in the next lecture. Have a great day.